Okay, all right, everyone. My name is Karan Gupta, and today I'm here back again with a really nice theory related to the thermal analysis. And the best part of this theory is going to be we are not only going to learn the theory, but we will try to do some of the example, whatsoever the theory we learn, and why I really force someone or any of the engineer to learn the theory first, because this is a basic understanding one must have. I mean, you guys can really try to learn these softwares while doing some of the examples, but theories literally plays an important role to understand how exactly things are happening, because in software one has to really provide a really important thing is to provide a good boundary condition, input condition to read what exactly it means. For that, the first and foremost thing is to understand the theory. So I just want to force you to always try to learn the theory first and then get into the software part of it, because software you can learn within like a week or month or even less than that, but theories are something that has to be taken into account in your brain. Each and every day you have to do revision, you have to understand. So being a mechanical engineer, we guys have to do a lot of things, we have to learn a lot of theories. So once you are really good with all the theories, let's say about solid mechanics theories, about thermal theories, about vibration theories, what's going to happen? You are strong enough in the mechanical engineering domain, and doesn't matter if the particular CAE position, so-called computer aided engineering position, or designing is another part of it. So you guys can easily tackle not only all the existing problems if you're in a particular role and your boss give you a particular thing that relates to a totally different theory. All you need to do is, you are already at a good end, you already know the software. Now you just have to simply understand the theory and then accomplish the analysis perfectly. So without wasting a lot of time, I just simply want to enter into the thermal part today. So thermal analysis. So one may ask, like, why exactly we need this thermal analysis? So this is to understand like how the temperature distribution happen inside a body or a system. So one may try to understand an analogy with different theories that we have seen or like in your academics. For example, let's say solid mechanics theory. So what's the purpose of solid mechanics theory, correct? So we try to give some, displacement, or rather than say we say some force, or we try to understand the displacement deformation, correct? Each and everything. I mean, that's more related to the stress strain part of it. Understand how much the deformation is happening, strain distribution. So here, when I talk about the same analogy with the thermal part, it is related to the temperature distribution. So what the first term comes is like, if we have, let's say, a particular body, and we want to understand what exactly the temperature is here, correct? Let's say if this is fixed, and or if there is some heat is transferred from this particular side, we want to understand what is the temperature distribution at this part, correct? So there are a lot of things that one can do if someone knows about these theories. So this is what exactly our main goal is for this particular, let's say, the lecture series. Understand the theory in a really good way, not going so much deep, but if still needed, then yes, take that part and try to understand more through a lot of softwares that, I mean, the so-called the surfing on internet, that's what is available these days, like, ChatGPT or some other AI tools to understand more into the deeper. But the first and foremost thing is, get a basic knowledge of it, then you can go ahead and expand your knowledge. Perfect. So as I told you, like, the first and foremost thing for us is what we have to understand these, the temperature distribution, either at a point or within the whole system or each and everything. No, the first and foremost thing that we have to understand is a very basic understanding of thermodynamics. If we don't have a good understanding of thermodynamics, then certainly will be a big issue. So what exactly we start with, like, let's say if in a body we have, let's say, like, certainly if we go to the molecular level of a system, then we have atoms or molecules. What exactly these atoms and molecules used to do, they used to just simply move from one place to another. Because of this movement, what exactly is happening, there is an increase in the temperature, or increase, the heat increases once this motion of these particles tries to increase. That's where we say there is a certain or sudden rise in temperature. Why it is happening? Because of this movement of small atoms inside a system or a body. Now when these body or when these atoms are not moving so fast, then we say this body has a low temperature, cold temperature, with respect to other body that where the atoms are moving so fast. Okay, that's one of the concept one has to understand. So when I say when the temperature increases, the heat flows from higher temperature to lower temperature. That's the tendency. So whenever there is a high moving particles, what exactly they will do? They will try to hit those particles those are not moving fast enough, correct? So once they hit them, they try to make it all the system into the equilibrium, and then we have the same temperature inside the body. That's what we say the equilibrium of a system, where all the particles are moving with the same velocity, with the same kinetic energy. Okay, so since I talk about energy, so which means in general we have two types of energy: kinetic energy, that's the virtue of the motion of the particles or the atoms; potential energy, that's the virtue of the height. Okay, because of that, now once we have in a system both kinetic energy and potential energy, the for the atom altogether, we say we have an internal energy. I mean, this is what we say as an internal energy. And when I say the increase in internal energy is due to the respect that there is a increase in high temperature, the increase in kinetic energy. Okay, so that's how you can understand how these are combined all together. Now if we go deep inside the conservation law, then we know that the change in kinetic energy plus the change in potential energy plus the change in internal energy is all equals to 0, which means if any of the, let's say, energy changes or decreases, increases or decreases, the other quantity has to balance it out. For example, let's say we take a two car, they both did a collision, in elastic collision. Then what's going to happen? The kinetic energy is converted into internal energy. So that's how we say the increase in the whole system when this both the car hit all together. What we see after hitting, the kinetic energy converts into the internal energy. And what's the virtue of internal energy? It increases the heat of it in the form of a heat increases. So again, this decreases, this increases. So that's how like the equilibrium of conservation is well settled, and this is known as a conservation law. Now we all know about Newton's law, correct? So we have three Newton's has given us three laws. Accordingly, thermodynamics also has like three laws in general, but there was another law added, that was the zeroth law. So let's talk about the zeroth law. So zeroth law simply let us know about the thermal equilibrium of a system. That's what we talked a bit earlier also, but let's take an example. So let's say in general I have a apartment where I have a room, that's name is A, then we have a gallery, and then we have another room called C. So and the gallery name is B. So what is happening? I open the gate of A with respect to the gallery, which is B. So what's happening? A thermal equilibrium is set up. I mean, the same temperature is being set up. I told you the theory earlier. And now A is in equilibrium with B. Now what's next we are going to do? Let's open the gate of C, and equilibrium is being set up with V and C. Now as a final temperature or final system, like both or all the three A, B, C are in equilibrium with each other. Again, A is in equilibrium with C also. Why? Because A is with B, B is with C, then A is with C. I mean, try to understand. That's what zeroth law used to tell us, the equilibrium, thermal equilibrium of a system. That's it. Now we have a first law. So what exactly first law used to tell? It tell us simply about the law of conservation of energy, nothing more than that. So what exactly we have to account is three terms into the theory, like the internal energy, then work, and then the Q, that is a heat. So let's say if I have a system, I applied a heat to this system. Let's say a Q heat is applied to a system. What's going to happen? Because of this, internal energy is going to change. At the same time, I can do some work, correct? So these are the two things that I can do when a heat is provided to my system. So there's a simple equation. We can say Q equals to delta U plus W. That's what we can see it here. Always try to remember this equation, nothing more than that. Apart from that, everything is going to confuse you, so always don't take into account. Apart from that, we also have like four different cases that we can deal with this particular conservation law, energy conservation law is. Let's say if my work done in a system is 0, whatsoever the heat I provided, what's going to happen is going to be converted into the internal energy. So Q is converted into the internal energy. There is no work done, which means I have a isovolumetric or isochoric process or system. When this internal energy is 0, then whatsoever the heat is provided converted into the work done, we say isothermal process. When we say there is no way to transfer heat inside the system, this is known as the adiabatic process. Means no Q can go inside and no Q can go outside. That's the adiabatic process or adiabatic system. Again, isolated, the fourth one I haven't discussed, but it's an isolated system where everything is 0. Okay, it's totally isolated. So whenever we talk about the heat is taken by the system is positive, heat is given by the system is negative. Okay, or work done by the system positive, work done on the system negative. Okay, so you have to understand these sign conventions. This is something necessary. Now second law, something really that we have to understand is entropy, concept of entropy. We have always seen a simple definition of degree of randomness. That is really confusing. One has to understand, when I say second law, yes, it is related to entropy. Now we will go in a different way. What is entropy? So entropy is, let's say whatsoever the system I have, let's say this is a system, I provided a Q heat and I am able to do some of the work, and some of the part of it is getting lost, let's say as a form of friction, as a form of sound or any other thing. So whatsoever this partial loss is happening to my system is known as entropy. Okay, that's the form of entropy. So which means if I say if this partial loss is equals to 0, this entropy, which is denoted by delta S, is equals to 0. And this is what the Carnot principle or Carnot engine was here. So they say, okay, whatsoever the heat you provide, Q, it's going to be converted into W. That's it. There will be no loss. In real case, that's not at all possible. So that's why we always have this delta S is greater than 0 for a realistic case. Okay. So now whenever you try to understand entropy, yes, it is the partial loss, and if you go, then this partial loss is the loss is going to spread to the system, and this is what we call the degree of randomness or spreadness. Okay, also of my system disorderness. And that's, it means like how energy is being lost to the surroundings. That's a simple definition. If there is no loss, delta is equals to 0. If there is loss, here there's a real case, is going to be greater than 0. Yeah. Now we have a third law. Third law simply tells us about the absolute zero temperature, which means there will be a temperature where these particles that we talked about earlier is not going to move at all. Temperature is known as a 0 Kelvin or minus 273 degrees Celsius. That's the lowest temperature anything can achieve, but in reality, none of the temperature, even cryogenics, cannot achieve that much lower temperature. Even we have accounted like minus 110 or something even less than that temperature as a lowest temperature, but this is non-achievable. Okay, but if it is achieved, then there is no motion of the particle. Now here comes the main part of our theory. There's a mode of heat transfer. So we generally have three types of heat transfer. One is a conduction, one is convection, one is radiation. As the name itself suggests, the conduction means the transfer of heat through a single medium. Here, convection means through two different mediums. Here, we are simply talking about the emission of the heat. That's a different concept. Again, you may say, Karan, you didn't tell us about anything about the medium. We all know medium. So, medium is a solid, liquid, and gas. Correct? This is what we have studied in our high school. That's what we say the different medium. So when there is a single medium, then conduction, convection, two mediums, radiation is emission. Okay. Now let's talk about a bit more into conduction. So conduction is further divided into the steady state and unsteady state. So steady state simply says this temperature that you are going to tell or deal with is not going to vary with respect to time. It's gonna be constant. Then unsteady state says, okay, I am going to deal with the time. So which means if the temperature is going to change with respect to time, I will try to let you know. So I think this is much more realistic, isn't it? Which means, let's say if a body is heated some from here Q, and at time t equals to 0 the temperature was 200 degrees Celsius. After time, let's say 10 minutes, I want to check here what's the temperature. It dropped down to 50 degrees Celsius, so which means we are talking about unsteady state. So now if we bounce back to steady state, then we have two conditions: whether the body is generating heat, QG, or whether it is not generating. If it's not generating, it is, I mean, for sure that's one of the case. If it is generating, then that's a different case. Now you might say, Karan, okay, let's deep inside what exactly the conduction equation looks like. So for equation for 1D program, for 1D, let's say if it's a wire case, in that case we have a homogeneous and isotropic. If we have a homogeneous and isotropic material, then heat conduction is equation is by a Fourier law. What exactly this Fourier law used to tell us is all about the heat transfer or heat conduction is equals to minus k times A times gt over dx. This k is the thermal conductivity, and we know with a simple analogy of electrical stuff and each and everything, or the stiffness, if you remember, then this k tells how much the heat is conducted by my material, which means it may vary with respect to different materials. K, a material property. A is the area wherever we are dealing with, our body or a system. Dt is over dx is the temperature gradient with respect to the defined uh, distance that we have taken into account. And then we have a negative sign. It tells that the heat flows from higher temperature to lower temperature. That's the simplest equation one should always remember. Now uh, you might say, Karan, okay, why shouldn't we go a bit more deep inside into it? So in general, we don't have 1D state. We always see highly irregular 3D state in front of us, correct? So for that, we have to deal with the 3D condition. In general, in that case, the temperature will be a function of space and time. So when I say space, the space can be like a 3D, I mean a Cartesian coordinate or rectangular coordinate system, where we simply say x, y, z and represent by the Cartesian coordinate planes. uh, we also have like spherical, and we also have cylindrical coordinate system. These two are much more complicated, but depends like how your geometry is being defined. Accordingly, they might be really useful. So now the point is, now here I form a equation, unsteady state response here, a highly nonlinear in general that varies, the temperature varies with respect to time. So here we have this gradient. This gradient here, I just simply say in a rectangular coordinate system like x, y, z, how it varies the temperature. It is the heat generated, as I told you earlier. Then we have this k, we all know, and this is alpha is thermal diffusivity. It tells us how much the storage capacity, the heat capacity of my system. Okay, so here comes the two cases: when conduction is happening without heat generation, and when conduction with steady state. Either without, I mean this can be unsteady state, this is steady state with heat generation, without heat generation. Different cases as per your problem, define it. Again, thermal resistance, we all know this is a simple resistance that we can easily understand from electrical part of it, like electrical resistance. Here we have thermal resistance, which means it's going to restrict our heat flow. The heat is going to be restricted. Why? Because of the thermal resistance of my body. Now, what is heat flux? We all know how much the heat flows from a particular unit area or for a particular area. That's what the heat flux is. Now, we already know what thermal conductivity. I already told you, like this actually depends on the material heterogeneity, or whether the material is heterogeneous or homogeneous. Accordingly, in xy direction, these properties are going to be different. Now, unsteady state. So unsteady state, where we have to deal with the temperature that varies with time. Again, here we can have two systems. One of them is a periodic system, one is aperiodic system. So periodic system is when the same cycle is happening, like in like addition of heat, doing the work, and then this and some rejection also of heat. This cycle is repeating again and again, like in a periodic manner. That's where, like we say, the periodic in heat engines, for example, it's gonna happen. A periodic is when only a single cycle is repeating. For example, for a particular material like forging, forming, or manufacturing process, a periodical cycle happens. Now, how we can define unsteady state in two different cases. One is a lumped parameter, one is a Heisler chart. Again, I don't want to go too much deep inside it, but if someone wants to understand what is unsteady state, then we have to understand lump parameters. Here two conditions comes into the action. One is a temperature gradient, we know about dt over dx. One is a temperature that varies with respect to time. Okay, so again, here the temperature gradient is constant for lump parameters and temperature is varying with respect to time. Okay, but in Heisler chart, like in that particular case, both varies. So what exactly we have to do, we have to follow a particular let's say chart to solve it. And there are other conditions also, like this Biot number and other things. I don't want to go much deep inside into it, but still, if you are good enough to understand this, go ahead. Now, concept of fins. One may ask, Karan, why exactly we need fins? So actually, the fins are something so as to increase the heat transfer of my system. So for example, if I have a main body right now and I want to transfer the heat, generally without fins it was happening, but it wasn't so fast. Now, why shouldn't I add some fins and try to see whether the heat transfer increase or not? So that's why we try to introduce heat, I mean the fins. And what exactly they do, they transfer heat to the surrounding medium and through convection. So convection we haven't studied, we will see a bit late, I mean soon after some time. So these fins are of different types, I mean long fins or short fins with insulated tips or non-insulated tip. Accordingly you have to define. Now one may ask how we can define the performance. Performance can be defined either showing the fins effectiveness or fins efficiency. So fins effectiveness means whether adding fins is effective or not. This tells us, okay, there might be a case you added a lot of fins to the system and at the end of the day it's not that much effective. So this is simply a loss of the, I mean cost, loss of the manpower and each and everything, correct? So this tells us the effectiveness. Fins efficiency is simply how much the heat is transferred. Okay, for this two, with these two conditions we understand the fins performance. Now the important part is the convection. Again, so convection tell us the modes of the, I mean we already know about convection. It is the mode where the heat transfer takes place between two mediums, the solid and fluid. So heat transfer rate is given by Q equals to H into A delta T. So H we know it is a heat, I mean the convection coefficient, convection heat transfer coefficient. A is the area where we are talking about. Ts is the I mean the surface temperature where we are interested, and T infinity is the surrounding temperature. So if we already know solid, we know about convection. For fluid, we generally say advection. When we combine, because convection is in two mediums, when we combine both of them, we say it is a convection, that is a bulk motion, transfer of the bulk motion of fluid. Now, very simple case, the convection is further divided into the free and forced type. Free, we all know, like here the transfer of heat is happening due to the natural, I mean the difference in density between two mediums, and the flow of heat is happening because of the simplistic difference in the density. And when I say about force, which means not only this is happening, let's say the difference in density, but I put some external source, that can be a pump or engine or something, a blower, anything, so that my heat transfer increase. So that's we say like force convection type of it. Now one may say like what exactly are the different types of flow? So there are certainly laminar and turbulent flow. So these are mainly different types of theory, I mean there are certainly different types of numbers, theories that define these laminar and turbulent flow in general. So we will not go that much deep inside it, but we will try to understand a quick overview what are these different numbers, a quick introduction. So whenever you see a Reynolds number, so what exactly they tell, it tells a particular value. For that particular value, whether my flow, the heat flow or a hydrodynamic flow, okay, the fluid flow is going to be laminar or turbulent, or the transition in between of those. Then we have Prandtl number defines the fluid property. Nusselt number is defines the convection type, and there are some other number also, we are not going so much in detail, that defines the free and force type. The motto is very clear for our, I mean, what exactly we are doing, we try to understand the heat transfer coefficient H as well as Q. Okay, that's what our uh, main motto is. When I talk about force convection, it if it is happening through a plate, like from a plate the heat transfer is happening, then we are interested always in mean film temperature. When in conduit, which means through pipe or duct, which means we want bulk mean temperature. Now here comes two concepts, as I told you, like hydrodynamic boundary layer or thermal boundary layer. Again, both has its independent laminar trans, I mean the turbulent flow. So make sure once, as the hydrodynamic itself tells, it is dealing about what? Fluid part. Thermal means this heat part. So once both of them are fully accomplished in a flow, then we say the flow is fully developed, unless it is developing in a pipe, for example. Let's say free convection, we all know it's naturally done because of the difference in the density. And when I say this particular Rayleigh number is less than 10 to the power 9, we say the system is going to have a laminar flow. And if it is greater than 10 to the power 9, we would say it's a turbulent flow. There are some certain different conditions also, like whether my system is inclined or not. According to the orientation, we find it out these flows also. Important concept, what exactly the industry need is heat exchanger. What exactly, I mean, they want is, they want to exchange the heat, correct, from one fluid to the another fluid. That's what their main motive is. So what exactly we do, it can be done in three different types. Like what exactly we have done so far, I mean in general, like in our life, we try to mix both hot and cold. That's what you understand, the one of its type, heat exchanger, that is a direct mixing. There are two other, storage as well as direct transfer. Storage means we store one and then flow the another one. Direct transfer we'll try to see here. So when we will see the first type here, we have like the direct transfer. So what exactly we do, we try to have some solid separation between two fluids, which means we again might have the conduction transfer as well as the convection transfer. Both transfer is going to happen. So the first one is the parallel flow. When, let's say, the hot fluid as well as the cold fluid are flowing or transferring heat while flowing parallelly. Okay, parallel flow, like that. In this way, again, the heat transfer is happening. The second one is the counter flow. When hot is going this way, cold is going this way in opposite direction, there's a counter flow. Cross flow, one is in vertical direction, one is in horizontal direction, and then the heat transfer is happening. Now you may ask, what's the purpose? Actually, we don't want to understand how the things are happening in between. We are interested in the final converted temperature. I mean, if my motto is to convert my hot temperature into a cold fluid, that's what, like, I need the final temperature. That can be achieved through two different ways. One is a logarithmic, one is a arithmetic. Okay, so with respect to these two temperatures, we can find it out to the final converted temperature. And you might see, like, most of the time logarithmic mean temperature difference is being used, because since it is more efficient and a lot of heat exchangers are designed with respect to the LMTD only. So in industry you will try to see this particularly more into the action. Now certainly we also need to understand, like, the effectiveness of these heat exchangers. So which means, like, we have to understand how many units are needed to convert the final temperature from, let's say, hot to cold. So this is known as the NTU. So how many units are needed? So this is define the NTU defines a unit. Now this is all about heat exchanger, and here comes the radiation heat transfer. So we'll try to understand this in a quick session, that radiation tells us how much is the amount of heat emitted by the body. I mean, how much a body is emitting the heat. Okay, that's the way of the heat transfer radiation used to do. So the governing law is known as the Stephen Boltzmann's law. I don't want to go into the depth, but it defines, like, this particular governing law is defined for an ideal body, and for radiation the ideal body is defined as a black body. So here the concept is to understand the emissive power of the body. Emissive, like how much it is emitting the, so the total amount of heat radiations that is being emitted from a black body. The governing law is defined with respect for this is the Stephen Boltzmann's law. Okay. Now, we have to understand a body can not only absorb, but it can reflect as well as transmit these sort of the radiations. So when I say these radiations are being transmitted, it has some of the intensity. I mean, if in general these radiations have some of the intensity, and when I talk about intensity, then certainly the another word that comes into my mind is the wavelength. So let's say these intensity have multiple wavelengths, but if I restrict one of them wavelength and then try to understand more about it, then we say that radiation is known as a monochromatic radiation. So that's it. I mean, it's a totally different theory and a lot needs to be discussed. So this is all about the thermal analysis theory and are good enough to understand or to do one of the example. So next we will try to understand the same with respect to our example in Abaqus software. All right, everyone. So now we are going to see one of the example for whatever the theory that we have learned so far. We will try to put it into the software point of view. I mean, how we can do those analysis and try to understand like how exactly the temperature distribution goes from one surface to the another surface. So that's a really good way of visualization whatsoever the theory one has learned. And this is more related to heat transfer. And I will simply say like that's the main scope of this particular lecture series, so as to give you a good understanding rather than you cannot see or even from your naked eyes like in the day-to-day heat transfer, but to just try to use those theories and particularly have it like the practical experience with the help of software. This is what exactly my main goal is. I have seen a lot of people like those who don't understand the theory and try to dig into the software part. Somehow they are able to do the analysis, but they don't know what exactly is happening at the back end. So please make sure to learn the theory first. That makes you much more expert or experienced and what exactly the problem statement is, because make sure like whenever we try to solve any problem with the help of the softwares, we really have to know about the input condition, the boundary conditions, and everything comes into the knowledge when you know a really good theory. It's not only the theory of the, let's say, the theory, I mean the heat transfer, but also some of the user interface of the software also, like how to apply it perfectly. So make sure like everything are aligned so that you guys are good enough whenever you try to introduce your skills to any of the company to accomplish their task. So make sure this is a really easy example of heat transfer. Like we are just simply going to check the temperature distribution from one surface to the another surface. We can easily deep or like get into the complicated heat transfers problem since we have already learned a bit of the theory, so we can get into it. So now the next screen that you will see is going to be the problem statement. So what exactly we have to do? We have a square 2 meter by 2 meter two-dimensional plate, like 2D plate. It has a thermal conductivity of 35, and the top surface is maintained at 400, that's degrees Celsius. The other three sides are maintained with a temperature of 55 degrees Celsius. So what we have to do, we have to determine the temperature at the center of the plate, all fine, and plot the temperature distribution from top to bottom. So here we are looking for the like how the temperature is flowing from hot to cold. So we have to check it out from with respect to the center line. Okay, through the center. Okay, perfect. So that's what the problem statement is. And also make sure like when we do these analysis, particularly into the Abaqus, so we have to understand the unit system. So the set one defines our unit in degrees Celsius, and set 2 defines in Kelvin. So since our problem statement was in degrees Celsius, so we will take the unit or the set one. We have to set the work directory. That's by default is going to be temporary, but you guys can define as per your convenience. So let's quickly dive into it. So these are like some of the procedure, like some of the drop down way or a systematic way to address our problem. So we have to create a planar part, and we'll try to switch those systematic approach again and again to understand like whether we are doing correct or not. Okay, so let's say we have to create our part. So let's say this is a plate and 2D deformable shelf. All fine, this is what we need. We want like how much it is going to be, like 2 meter by 2 meter. So here I define 2, and here again I define 2. Perfect. So that's what like our part is ready. And what next we have to do, we have to create the sets. Okay, so we have to create like different sets here. So we simply go to the part here. So we want the surface where exactly our temperature is going to be 400 degrees Celsius is created. Then we also need the side surface, and if I continue, make sure to press the shift to select different side of it. And I guess there's some issue. All fine. So these all three sides are selected right now. There's a side surface, and once we create the mesh, we will try to account also the center point as well as the center line. But yeah, that's going to be the next part. So we have to create datum plane, and that's where like we have to create datum plane and create partition. So either you can create the datum plane from this particular module, or also the partition from here, or there is also another option like you go to the tools. Here is quite straightforward. Just go to the datum. We want plane. We want midway between 2 points. So I select 2 points, and these are my 2 points, and another one I want to select it like this. Perfect. So my data plane is ready. What I have to do is to create partition. Again, we go to the tools, partition. Then we can create the partition by these many methods. So we already have a data plane with us, and we want this to be get parted. I mean the partition. We create partition. All fine. So partition is all done, everything is all fine. Now we have to create the material. So now from part we go to the property, material assignment. Okay, let it be material one. So we are not going to assign the mechanical because we are not dealing with the solid mechanics part. We are dealing with the heat transfer part. So conductivity was 35. That's what given to us. And then what we have to do is okay, create section and assign the section. So we have to create the section. Section one, let it be solid homogeneous. Material is already defined for us. Let's assign the section. The section is defined for us, all fine. So when it turns green, which means like everything is all fine, like the section is being assigned. Now after this we have to create mesh. In general we used to create mesh later on in solid mechanics, but here since we have to define the center point and each and everything, so it's all fine if you create the mesh right away, unless like this is the hierarchy, but you can easily get into this mesh part. So whatsoever it is shown, it's all fine. Apply, but I really want it a bit smaller. Apply. Okay, then you can do the mesh here. Okay, I'll find the mesh is perfectly aligned and it is a quad mesh. And what next is okay, so make sure like the family of these elements should be heat transfer. It's not going to be the plane stress, so we have to select heat transfer particularly here. Geometric order, linear, quadratic. Okay, if you assign quadratic, some I mean you might get a good accuracy, but for now linear is all enough, all good enough. Perfect. So this is what we have defined, and what next we have to check is we have to create node sets. Okay, that's what I told you earlier. So again we go to the set, we say this as center point, let it be the okay, so this is the center point, all fine. Again I want to create the distribution, temperature distribution. For that I will select all these nodes again. I say like top to, let's say, bottom, and I need to create unsorted nodes. I just want it before. Hold on. Here we have to select the free part. Okay. The nodes level should be at least okay. So I guess need to redefine it. Okay. Here we go. Here it is. Top to bottom. Make answer free. The node level should have at least one row. Okay. At before. Perfect. That's where like I have to define it. Now I think everything's fine. But yeah, there is some bit of modification that we will do later during the post-processing part. Where we have to create the path. Okay, that's what we have to do it. Now we have to do the assembly. So since we have already one part, we don't need to define anything else here. Okay, what next we have to do? We have to define the step as a heat transfer. So here comes the difference. So you go to the step. So we define as heat transfer. All fine. And we don't have to take the static journal here. So we have to define heat journal. It's a steady state problem, and let it be all other things to be by default. Perfect. So step is all defined. We have to create the load here, and load is create boundary condition. Okay. So the first boundary condition we want to create like the top, and I guess okay, all fine. Create the reasons. Okay, sorry. Since we have to create it, we have to set top, and the best part is like we have already the set defined for it. So simply we go to the set. We have a top surface for it. We can highlight also. Yes, this is what exactly I want, and I want this as 400 degrees Celsius. Perfect. We have to create other side also, like this side surface, and that's what we need to define. Again, we already have a defined set that's going to be the side surface. Perfect for us. And it's going to be 45. All fine. Perfect. So I guess we are all done with as of now with this data, and we have to create a job. It's so much simpler. We go to the job, and either you create it from here. We can say heat transfer theory. I don't know. It's going to say yeah. Perfect. So we just try to run this heat transfer theory case. Now it is also asking for the history output, but doesn't matter for us because we will be looking for the field output, and we have already defined our center point. So it's the easy one, so as to understand the different part of it. I mean the different heat flux, nodal temperature gradient. It's not going to take a lot of time. It's going to be very fast. So if you guys want, you guys can monitor also, like how much time steps gonna take. But since it's a really linear problem, it's not going to take that much of time. In a single iteration, it's going to solve. Okay, that's it. So it's going to solve it. Perfect. So our analysis solved. Let's go to the result part. Perfect. So here is the result one. This is undeformed. This is deformed. So okay. So what are these part here? So this is a temperature gradient. That DTODX that we learn about it. This is heat flux. Again, I told you in the theory. This is the nodal temperature. That's what we are interested in, correct? I mean, how the temperature is being distributed in this particular plate. Let's go to the problem statement. What exactly they want is the temperature at the center of the plate. Perfect. So what we have to do, just simply go to the XY plot, field output, or do we field output, continue. What we need is the nodal temperature. This is mixture, like you might have integration point, but we are defining it for the unique nodal. And we have to go element sets. Everything is defined for us, node sets. So we go to the center point, we say plot. Okay, so let's cross it. So what exactly is the maximum temperature that we see at that particular node at the center of it? Well, it is actually 141 degrees Celsius. That's it. And what else we need? We need to define a path also, so as to make how the temperature distribution goes from the top to the bottom. So again, you can go to the tools option, you can go path, and you can create. Okay, let it be the path 2. Continue. Make sure we have already defined it earlier, so we are not going to define it. We will try to bring it back here. So we define it before, and that is top to bottom. We just put it here. All fine. So here, like you have to turn on the option, like the visualization option from the options itself. Let's say, I mean, you go here, and what exactly you guys have to do, just go to the common part and normals, labels, show node labels. So I mean, this is a bit confusing initially, and you can play with like all the font and each and everything. Like let's say I don't want that much big option, I want to apply it here. Okay, if you want even much more smaller, so you can say 4 out of it. And yeah, so here you can see at the top it is 2, and if we try to check it out in our path, whether it is right or not. So again, we go to the path, create path, and let's continue this path. We want at before, as I did earlier, top to bottom. This is what I want. So you can see here, like just a minute, this 2 is a bit, it's not arranged. So 2 is coming at the top part, and if you see the below part, then after 1 it is 7. So we have to arrange a bit. So we have to just simply make it 2 at the end, and that's how like my path is defined. And now I want to plot it, my nodal temperature here. So what I have to do, again, go to the XY data. Since I have the path, so continue, and okay, so it asks for path 2 for us. So this is where like our path is defined, and that's it. We need to plot it. So what you can see, like the top surface was having 400 degrees Celsius, and later on, if you go downward, it was set to 50 degrees Celsius. So this is what like temperature distribution goes on for the middle path of it. Like that's what the problem statement tells us, like the temperature distribution from top to bottom. This is what we created, passing through the center. So I guess that's what we do in journal in the heat transfer. So there are going to be really complicated part also. We can do like heat transfer. We can do even composite walls heat transfer, and what else? Like there is a lot of possibility to even accomplish the steady state response. So that's it for this particular part. I hope it's not going to be too much lengthy, but it really makes a practical aspect of whatever the theory that you have learned with respect to the software. So that's it. Thank you very much. Have a nice day.